Yes.
Okay, thank you. Well, hi everybody. I want to start by, of course, thanking the organizers for this opportunity. It's really a pleasure to speak to you today. I'm sorry I cannot be there. It would have been great, but I couldn't make it. Today, I thought I could talk a little bit about some of the main things that I've been working on in the last couple of years. I would say, particularly in the field of the Halo galaxy connection, and more specifically regarding Halo and galaxy assembly bias. So hopefully that will serve as well as a sort of a review of the field, at least from the perspective of the works that I've been doing during the last years again. But before that, so the title of the talk is the Halo Galaxy Connection, a multi-angle approach. Before that, I really wanted to say a few things about USM, Universidad Técnica Federico Santa Maria, here in Chile. These are really exciting times here. We are pretty much putting together or building a department of astrophysics from scratch. We have very few professors yet. We have 2 nodes, Halo Galaxy Connection and Stellar Astrophysics, but we hiring more people this year and also next year. So if you're interested in visiting, please let me know. It would be great. Okay, so here's the little outline of my talk, and on the right-hand side there are some of my main friends in the Friend of Friends meeting. Facundo Rodriguez, Celeste Artale, some other people, particularly Nelson, right there in the middle, populating small dark matter halo there. Anyway, so here's the outline. I'll start with an introduction on things that, of course, you already know pretty well. Then I'll continue explaining a little bit what secondary bias is, in particularly halo and halo assembly bias, sorry, and also spin bias. Then I'll talk about the physical interpretation of Halo assembly bias. Maybe this is where kind of like the review part of the talk kicks in a little bit. I'll talk a little bit about the shape of the Halo mass accretion history and how that can be a good link with galaxy properties, and also in terms of assembly bias. I'll talk about spin bias, which is the other secondary dependence of Halo bias that people have been, well, with concentration as well. It's a little bit of a long shot to observe it, but I'll explain a few ideas there. And I don't think I'll have time to talk about machine learning, but I'll give you just a reference there of a paper that we just submitted. Okay, so here's the, let's start with the introduction, of course. Of course, you all know that the theory of structure formation in the lambda CDM cosmology predicts the evolution of dark matter dominated density field and the formation of collapse objects. This field, as you know, is believed to originate from tiny fluctuations in the early universe that then expanded due to inflation. And we know that, of course, this structure grows through gravitational instability. But it's also slowed down by the opposing effect of dark energy, right? So these perturbations, of course, grow, then at some point disconnect from the Hubble expansion, collapse, and virialize to form dark matter halos. I cannot use my pointer here, which is, but anyways, I think it's fine. Then, of course, we can, I think in the Halo Galaxy Connection, the way I see it, at least a personal view, we work with like 3 different fields. If you want, you have the underlying matter density field, which is of course a continuous field on the left-hand side. At the center, you have the dark matter field, which is a discrete field, where we have also characterized the different properties of halos. And of course, we have galaxies that we can observe, or we can also model through hydrodynamical simulations. So we have also measured a bunch of properties from them: stellar masses, luminosities, colors, etc. Right? So, of course, here what we want to do is to connect these two fields here, the dark matter, halos, and galaxies, their properties, and of course in the context of the large-scale structure of the universe, right? So here, as you know, it's where a deterministic bias can be defined that relate the densities of the different fields here, and we know that both that halos are bias tracers of the underlying matter density field, and galaxies are bias tracers of the halo field and the underlying matter density field as well. Okay. Now, as you know, there's a main dependence of halo bias, which is again a way of characterizing or describing halo clustering, and that is basically halo mass, of course, right? That's the main dependence, and it can be shown, of course, from several formalisms like structure formation formalisms like Bresch-Schechter or Scheff and Thurman. It enters through the peak height of fluctuations, as you know, that it depends on mass. And we have a good idea of what the dependence on mass is, of course. Okay, and the a good illustrative way to see it is provided by the what's it called, the peak split background model, where it's modulation what causes this dependence. The fact that the large scale field background enhances the probability of forming halos, and that produces this dependence. But what I wanted to mention is that we have other dependencies of halo bias, and this is generally speaking what is called secondary bias, and in particular the dependence on the assembly history of halos is called halo assembly bias, as you know. Here's another illustrative picture from this recent review from Wechsler and Tinker. These are halos at the same mass at the same mass being. On the left-hand side, you have older, higher concentration halos. On the right-hand side, you have younger, lower concentration halos. And of course, if you put some faith on it, you can see that the clustering amplitude or the clustering properties of them are different, right? At this fixed halo mass, right? The left-hand objects trace better the underlying matter density field as compared to the right-hand objects. So again, halo assembly bias can be defined as is mentioned there. At fixed halo mass, halos that assemble earlier are more tightly clustered than halos that assemble at later times. And this is okay. This is again, the left-hand side is a way of showing the main dependence of halo bias, the dependence on virial mass, on halo mass, from this work from Jeremy Tinker, 2010. You can see obviously how the bias increases with mass because it increases with peak height. And on the right-hand side is a way of showing actually this halo assembly bias trend, right? Which is not the standard way of showing it, but I think it gives more information. On the x-axis, you have halo mass, and here on the y-axis, you have the scale factor at which halos form half their masses, right? So that would be like a formation scale factor, equivalent to a formation redshift or formation time. And you could see that at low masses, there's of course a separation in bias. There's basically different, a whole range of biases. Whereas when you go to higher masses, it converges to similar values of bias. Here, of course, what is called, the bias is measured on scales between 5 and 15 megaparsecs over 8. I'm already thinking that I won't have time to say everything that I was gonna say. Anyways, this is a paper that we did a few papers that we did a couple of years ago. This is another way of showing this. Here I'm showing on the left-hand side is the assembly bias signal. Of course, I didn't mention it, but this has been shown by, of course, many researchers during the last almost decade. Here we use the multi-dark simulations to provide a better measurement on a larger mass range of both the assembly bias signal and what is called the spin bias, halo bias signal on the right-hand side. And what you do here is you basically compute the relative bias between two populations of halos. They are split by a given halo property, right? The left-hand side, it would be the age of the halo. On the right-hand side, it would be the spin. But you basically use quartiles to map the whole distribution, and you compute the relative bias. So if the relative bias is 1, it means no assembly bias or spin bias. If there's a difference in bias at fixed mass, then you have a signal. Okay. What we show in the right-hand side is the spin bias signal is a little interesting because it crosses over at around 10 to the 11.5 approximately. That is a very clear demarcation. Above that mass, you have higher spin halos being more highly biased at fixed mass, whereas that trend reverses at the low mass end. Okay, so I'm going to just briefly talk about, sometimes it's not mentioned, some of the physical origins that have been proposed for these trends, particularly for the assembly bias trend. Maybe the first key or the first element is the truncation of accretion for halos in the cosmic web, in different locations of the cosmic web. This is a work from Borsiskowski, 2017, using high-resolution zoom-in simulations. And he basically studied two types of halos, what they call, what they call stalled halos and accreting halos, right? So these stalled halos are halos that are embedded in larger filaments, right? And have stopped accreting or have seen their accretion rate being hindered earlier on because of the fact that they are actually in filaments, right? Where you have a privileged direction for the flows of matter, basically, right? On the left-hand side, you have accreting halos that sit at the nodes of in the cosmic web, right, and are fed by these thinner filaments, right? So these continue accreting, right? So these two halos here have similar mass, so that could produce this assembly bias signal, right? Because you would have higher bias for the right-hand halo in this case, which is closer typically to a larger halo. Okay. So that's one of the things. The other thing that is very related to this that people have looked at, again, I think is pretty much, if I'm not mistaken, almost the same thing, but being studied in a different way, is the tidal anisotropy of the environment. Again, this is for low mass halos, right? For lower mass halos where the assembly bias signal is larger, right? At the high mass end, again, the signal for assembly bias is not too strong. Okay, but what people have done is measure this alpha parameter, which describes the shear, the tidal shear, or the it's called the anisotropy parameter. And the larger alpha, the more anisotropic the environment is. So larger alpha would mean that we have halos in filaments. Lower alpha would mean that we have the halos are in nodes, right? As you can see, I cannot use my pointer here, but as you can see on the upper plot, right-hand side there. So that's how the alpha, so how bias changes with alpha, right? And what people have shown is that you know, at fixed mass, you know, different alphas gives you different bias, and that is related. Of course, that can be related with the fact that also at fixed mass, different secondary properties of halos would display different biases, right? So I guess this is not so much of a mechanism, more or explanation more than a correlation, but it's related to the previous one. And the other thing that I wanted to mention is splashback halos. Also, again, always low mass here. You already know what I'm pretty sure what splashback halos are. In this context, these are distinct halos, the redshift under analysis that recently went through a subhalo phase as they basically passed through the virial radius of a larger halo. Of course, in the process, they suffer mass tripping and they're small. But the thing is that by definition, by the definition, I would say they are close to larger halos, but they are lower. They have lower masses, right? So that implies that you're going to have a higher bias because the bias is determined by the bigger halos. The fact that these bigger halos lives in you know, highly biased environments, but this is a smaller halos. These are smaller halos, right? These are halos that were subhalos recently, right? So that can produce as well that that separation, that discrimination in terms of bias at fixed mass for at the low mass end. Okay. There's other mechanisms that have been proposed, like twin bias, gravitational heating, but these are, I think, the main two that I would highlight. So actually, with the students a couple of years ago, we looked into these splashback halos, and how they affect the signals, the assembly bias, actually the secondary bias signals. I think I didn't emphasize it before. I'm going to say it again. Secondary bias. I'm talking about, in general, the different dependencies that you can have at fixed halo mass. Assembly bias is a particular dependence on age, on the assembly history of halos. So, but here we investigated the spin bias signal. The first thing that we measure is that that we discovered was that crossover that I described before, around 10 to the 11.5 solar masses. The trend inverts, and well, in the top panel you can see how the signal varies as a function of redshift. You see that that inversion slides to lower masses as we move to higher redshift, right, until a point that it basically disappears at z = 1.5. And what we showed is that actually splashback halos are responsible for that, that very inversion of the signal, or reversal of the signal at the low mass end. Once you identify them and remove them from the sample, you basically remove this inversion of the signal, and you recover what you expect, which is I guess from the tidal torque theory, etc., which is that higher spin halos at fixed mass are more biased than lower spin halos at the same mass, right? This is just showing how this happens. Basically, what happens, if I remember correctly, is that you typically have more splashback halos at the low mass end, and these are typically these have typically lower spins, right? But again, these are subhalos. These were recently subhalos, so they live close to larger halos. So they have lower spin but higher bias, and that basically inverts the signal at the low mass end. So you can see them as contaminants, I would say, of the spin bias signal in this case, right? Okay, so that was a paper that we another paper that we worked that we wrote a couple of years ago. The other aspect of this analysis is maybe, I guess, the most, obviously, this is the connection with observations, is arguably the most interesting part is what is called galaxy assembly bias. This reflects the hypothesis or the potential fact that these trends actually manifest themselves on the galaxy population as well. So galaxy assembly bias is defined as the dependence of galaxy clustering on secondary halo properties at fixed halo mass. Okay, I would say this would be a kind of like a classical definition of galaxy assembly bias. There's been other definitions in terms of occupancy variations at fixed halo mass depending on secondary halo properties. You can also talk about galaxy properties in general, that depend on halo properties beyond halo mass. And there's other recent things like anisotropic assembly bias, etc. What we show with TNG 300 in this other paper is that, of course, when you, this hydrodynamical simulation, of course, is that at fixed halo mass, redder central galaxies tend to inhabit older halos. So the halo bias signal, as defined here, is transmitted to the galaxy population, right? That's what it's shown there on the left-hand side. Again, this is the relative bias, and I'm splitting the galaxy population by color and by star formation rate. And that's the brighter colors here, the orange and cyan would be the result of this splitting in galaxy properties. And on the background, you see the assembly bias trend that coincides very well with the galaxy trend. So of course, since since there's a connection between galaxies and properties, the assembly bias trend would the halo assembly bias trend would manifest itself, at least from the perspective of hydrodynamical simulation on the galaxy side. Now here, the typical thing that you do is you parameterize, I'm really running late here, you parameterize the assembly history of halos through this formation time, the time or formation redshift, the redshift at which half of the mass of the halo is created, is assembled. What we looked in this other paper that we published last year is actually we wanted to look into actually the shape of the mass accretion history, not so much this single parameter. Actually, we used a single parameter as well, but that reflects better the shape of the mass accretion history, the specific mass accretion history in particular. So we used TNG 300 and we computed this specific mass accretion history that is that expression that I have there on the left-hand side. Is divided by M peak in order to capture the relative growth of halos. It's normalized. And of course, we used M peak because it's supposed to be more stable. This is the maximum mass that a halo can attain or can that a halo reach in the whole history before that time that you're measuring it, right? So what we did is to parameterize it using a simple power law, as is shown there on the left-hand side. This was also made by Hearing a little later. So that plot right there shows a particular example, randomly taken as usual. Of course, one that looked good for this thing. It's basically the mass accretion history as a function of time, and you can see that it fits very well a power law. Beta being the slope of the power law. In this case, is minus 1.48. So here's some, so what we found is that many halos in TNG 300 actually are well fitted by this parameterization, their mass accretion histories. Here, what I'm showing on the left hand, what I'm showing these plots, it's for two different masses. And I'm showing the, the populations were of basically galaxies in halos, where their halos have steep, intermediate, or shallow betas, right? So slopes of the beta parameter. Shallower would be that the accretion history obviously is not as steep as in the case of steep, obviously. So what we can see is that the galaxies in halos, so basically they're halos, halos that have a steeper beta, more negative beta, assemble their masses earlier on than halos that have shallower betas, independently of the mass that we use. That is more easily seen on the right-hand plot there that I'm showing. Okay. Now the question is how beta connects to galaxy properties in general, right? This is what is shown. What is shown here. This is probably not easy to explain all this thing in a few minutes. So I'm going to just summarize it. Here I'm showing the star formation history, the gas fraction, and the stellar to halo mass ratio. And again, dividing, actually these are galaxies, but they're halos in steep, intermediate, and shallow betas here, right? So the bottom line of this plot is that there are a couple of things. What we find is that galaxies in halos with steeper betas, they tend to, as you can see in the top left panel here, they have their star formation history peaks earlier than for shallower betas, as you can see there. Their gas fractions drop also earlier, so they're quenched earlier. And their stellar to halo mass ratios also are larger for these steeper beta galaxies, right? Another interesting thing, one of the most interesting thing is that this parameter, the link with galaxies is more stable than when you use formation time, just the time at which halos form half of their masses, right? Where it's not as monotonic as it is, as you can see in the plots. You start seeing, curves that cross over, etc. So it looks like beta is a more stable link to the properties of galaxies. You can also look at other things like color, and again, you find similar results for color or for the quench fraction on the right-hand side. I'm going to skip this quick. And of course, then you want to also see how assembly bias depends on this parameter, which is the most natural parameter, I think, to measure assembly bias, because assembly bias is basically the dependence on the formation history of halos, right? And of course, you can see here, this is for a particular mass beam of M peak at redshift 0, 11.5 to 11.7. And on the top panels, you see high beta. On the lower panels, you see lower beta. And these are two different redshifts. And you see that particularly at a low redshift, obviously, the low beta, steeper. Low beta is more negative, so steeper galaxies, or galaxies in halos of steeper low beta, are more tightly clustered, easily seen than in the case of the high beta objects. So we can also measure here the assembly bias signal. And this is what is shown here. There's several things here that can be mentioned. We basically measure the redshift evolution of assembly bias here. On the left-hand panels for central galaxies alone, on the right-hand panels for central and satellite galaxies together. Again, this is on scales of between 5 and 15 megaparsecs over H. And the upper panels are we are binning in mHost, instantaneous Halo mass here, whereas the lower panels is mPeak, basically, at redshift 0. Yes, and there's a few things that can be said here that are interesting. When you add satellites, the assembly bias signal increases a little bit. That's interesting. The other thing is that when you look at the, I'm basically summarizing the plots, when you look at the evolution in redshift, what we're doing here is follow basically the merger tree. So this would be the evolution of the assembly bias for the progenitors of redshift 0 galaxies, right? You're not basically looking at the entire population independently at each snapshot, but you're basically measuring assembly bias kind of like along the merger tree here. And when you do it that way, assembly bias actually increases with redshift, as opposed to decreasing, which is what it had been shown before for the assembly bias when you just consider the populations at different redshift independently. That particular dependency on redshift comes from the fact that assembly bias at fixed mass, understood that way, it's basically, it depends on peak height. It can be normalized basically, or normalized is not the word, but the dependency comes from peak height and not from mass, right? In this case, it's different because as we are actually measuring assembly bias for the progenitors or redshift 0 galaxies, these progenitors are more massive in the case of lower betas than in the case of higher betas as we move back in redshift. So this is a little hard to explain, but I mean, if you look at the plots and think about it for a second, I mean, you see it. Yeah? So that's another interesting trend that we found, and this will be basically the here what I'm just putting the what is it that we're showing here? Yeah, the redshift evolution, but integrated for a particular mass being. You can see how it increases as a function of redshift. So these are just some highlights. The slope of the beta is advantageous as a means of describing Halo evolution, that it displays monotonic and smooth relations with important galaxy properties. It also shows interesting assembly bias trends. One thing that is interesting as well is that actually here the assembly bias signal is actually a little larger for formation redshift as compared to beta, and I think this beta parameter can be incorporated in Halo galaxy connection models such as SHAM and HODs. We are already trying to do those things. Well, I don't have much. How much time do I have? Sorry.
You have 5 more minutes.
5 minutes. Okay, so I'm going to just mention something real quick. Of course, the quest here at the end is to measure galaxy assembly bias or secondary bias in observations. This has been hindered by a number of different uncertainties and selection effects, cluster identification uncertainties, all kind of stuff. There's a lot of claims. I myself have also contributed to the confusion, as many others in the field. But there's many different claims here. It's really something that is not established yet. Actually, every time that I'm going to give a talk, that very week, there are 2 more claims on like today, there are actually 2 more claims on assembly bias, on the existence of assembly bias. But I'm going to leave this discussion there. This is not really established, and I'm just going to mention that we also try to think about ideas on how to actually measure the other trend, which is a spin bias trend that I showed before. Here, that plot is without actually removing splashback halos, but you could see that at the high mass end, the trend is pretty large. I mean, the difference in bias is pretty large for a cluster like halos, which are supposed to be the ones that are easier to detect. That's the plus. That's the advantage that spin bias has. The disadvantage is that it's very, very hard to measure spins, obviously in observations, right? Angular momentum of halos. But just very quickly, we did a little bit of a analysis last year, also using Illustrious TNG 300. What you see in Illustrious TNG is that, as is shown in that plot, is that the angular momentum of the gas in halos, it is correlated with the angular momentum, which is expected, of the dark matter in halos, as is shown there. So we thought that maybe the Sunyaev Zel'dovich effect could be of help here. I don't have much time to explain it, but I think you all know what the Sunyaev Zel'dovich effect is. You have CMB, low energy photons coming from the CMB that are inverse Compton scattered by electrons from the hot gas of clusters, right? And that signal can actually be measured and have been measured, particularly for the thermal effect, where the scattering is produced by random motion of electrons. The kinetic Sunyaev Zel'dovich effect is much harder to detect. It hasn't, I think it has been detected in a few cases only. So this is really a long shot, but I mean, it was fun to try to see, to do a little bit of a prospect here. Anyway, so we measured this with, we modeled this with Illustrious TNG for the Sunyaev Zel'dovich, sorry, for the kinetic effect. You expect, because this again is produced by two types of velocities, the bulk velocity of your cluster and the rotation of electrons, since they are spinning, the coherent rotation of electrons in the cluster, right? So you expect a dipole of the signal, as you know. So we did find the dipoles, and then we tried to basically, measure, actually analyze how these, the signals, both the kinetic Sunyaev Zel'dovich signal and the thermal signal. Well, I'm actually going to explain it well. Here on the top panel, that's the relation between the thermal effect signal, integrated signal, and the gas mass and the virial mass. On the lower panel is the same for the kinetic Sunyaev Zel'dovich effect signal, integrated signal. Okay, this is only the rotation. We subtracted the bulk velocity of clusters just to see what the rotational signal is. Okay, and then of course you can see what the correlation of this KSZ signal is with angular momentum of the gas and with the spin of the halo. And there's not that much of a correlation, but there is a little bit, right? As you can see on the right-hand side there. Here I'm actually dividing the KSZ by the thermal, because the thermal is basically a measurement of the mass, and the KSZ would be a measurement of the angular momentum. So it's kind of like reproducing what the spin parameter is, right? And anyways, and then you can measure the spin bias, and you see that at least in simulations in TNG 300, although it's a very small box, is significant, the difference. But of course, here the problem would be, the observational part, whether this is feasible or not. I think in the future it could be, once we have larger samples of KSZ clusters. I think this could be, but I recognize a long shot, but it's an interesting thing to look at as an alternative way of measuring secondary bias with real data. So that's almost all. I'm just giving here this, this paper from some students from Sao Paulo. Actually, we look at the Halo galaxy connection using machine learning, using all different type of methods. If somebody's working on this and is interested, please drop me a line or write to these persons here, or take a look at the paper. I think it's interesting. And actually, that's it. I'm gonna leave you guys with the take-home message, and that's it from me. Thank you very much.
Okay, we have a time for a couple of questions.
Hello. Hi, Antonio.
Hi.
It's Aldo Rodriguez Paula.
Oh.
So perhaps I missed this, but which definition of assembly bias you were using? Because there are several definitions of assembly bias. And then, in your opinion, well, you know, there is the assembly bias that you can define by Halo concentration, by Halo accretion, by the age of the dark matter halo. And then, in your opinion, which of these bias are the best one for connecting the star formation rates, colors, the galaxies?
The best you can. Well, first of all, my definition. The definition I'm following here is the most straightforward one. Just a manifestation of halo assembly bias on the galaxy population, simply. So it's the dependence. Yeah, you're right that I didn't really explain it well, but it's the dependence of galaxy bias on halo properties at fixed halo mass, right? Which I know that there are other definitions like using HODs or several other things. Now, the other question in turn, you said which signal is more connected to galaxy properties? Is that what you said?
Right.
Yes. I would expect, of course, the assembly bias signal to be more connected. It's a good question, but of course, the assembly bias signal is the dependence on the accretion history of halos, and that we know is connected to the evolution of galaxies. So that should be the one that is more directly connected to galaxies, as opposed to, for instance, for spin bias. We know it's a harder one. Now, between concentration and age, I'm not totally sure, because they both related, right? You find different trends, but those two quantities are related. But either one of those, it would be from my guess. Yes.
Okay. Thank you.
Yeah. Sure.
Yeah. A question over there.
Hello.
Hi.
I'm wondering about the beta parameter, the mass aggregation rate
Yes.
you are measuring. This is a slope of the mass aggregation history. Yeah? So how does change with environment? Have you find this beta changing on high density or low density environments? And the second question is, how can be affected by mergers? Because this is just an average aggregation rate, let's say. Yeah? But when you have major mergers, this changes a little situation, I think. So
it does. Yeah, I think that's one of the reasons we use big mass, because of course I think if you use the instantaneous halo mass, that's going to be more affected to this type of things, right? But you know, the truth is that when you look at the mass accretion histories, they all fit very well. Most of them fit well with this simple model. I suppose we could actually take a closer look at that. I think that's a good idea. Like actually selecting halos that we know that are very affected by major mergers, and see how that do a better analysis on that we haven't done really. But at least the fits look pretty good, and it seems that beta is a pretty good description of mass accretion history. And we also didn't actually look at things that how beta changes with environment, but it's another thing that is interesting. Yeah, this was like pretty much the first analysis on this, but those are very, very nice suggestions that we can look at.
thank you.
Yeah, sure.